Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with stellar nurseries, the fragile beauty of the pillars of creation. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. Stellar nurseries represent the cosmic arenas where new stars take form, embodying the intricate process of stellar birth. These regions are often enveloped in dense clouds of gas and dust, creating a complex interplay of light and shadow. In this context, the pillars of creation emerge as striking formations, towering structures that cradle the very essence of star formation. Within this expanse, the interplay of ultraviolet radiation from nearby stars illuminates the surrounding gas, causing it to glow with various hues. The dense cores of these pillars serve as incubators for nascent stars, where gravitational forces draw material together, fostering the conditions necessary for stellar ignition. This phenomenon unfolds over millions of years, a slow yet relentless journey towards luminosity. The unique morphology of the pillars of creation is shaped by stellar winds and radiation pressure, which sculpt the gas and dust into captivating shapes. This erosion reveals the fragility of the material, as the very processes that give rise to new stars simultaneously dismantle their birthplace. Observations from advanced telescopes have unveiled intricate details showcasing the life cycle of matter in these regions. On the context of cosmic evolution, stellar nurseries play a vital role, influencing the chemical enrichment of galaxies and the formation of planetary systems. Each new star birthed from these pillars contributes to the ongoing narrative of the universe. The pillars of creation were first revealed to humanity in 1995, when the Hubble Space Telescope captured their ethereal forms against the backdrop of the vast cosmos. This region, located within the Eagle Nebula, became a focal point for astronomers and enthusiasts alike. Initial observations hinted at the presence of dense gas and dust, but it was the clarity provided by Hubble that unveiled the intricate structures of these towering formations. Scientific interest in the pillars dates back further, as early telescopes allowed for glimpses into the depths of space. However, the true significance of these pillars was not fully appreciated until advances in imaging technology made it possible to discern the finer details of the gas clouds and the formation of stars within them. Investigations into their chemical composition revealed an abundance of hydrogen and helium, fundamental elements fueling the birth of new stars. The impact of this discovery extended beyond mere observation. It prompted a re-evaluation of stellar formation theories, allowing researchers to refine models of how stars evolve from molecular clouds. Over time, the pillars of creation have become symbolic of the ongoing cycle of birth and death in the universe, a reminder of the fragility and beauty inherent in cosmic processes. This profound understanding continues to inspire both scientific inquiry and philosophical reflection. The formation of molecular clouds represents a critical stage in stellar development. These dense regions, comprised primarily of hydrogen molecules, are the sites where gravity begins to assert its influence. Within them, temperature and pressure conditions facilitate the consolidation of gas and dust, leading to the birth of new stars. These clouds, often shrouded in intricate structures, reflect the dynamics of their environment, influenced by factors such as radiation from nearby stars and the turbulence of galactic winds. Within this region, regions of higher density emerge, serving as cores for future stellar bodies. As these cores accumulate more material, they contract under their own gravitational pull, leading to an increase in temperature. This process initiates a delicate balance between gravitational forces and the outward pressure generated by fusion reactions. The moment when core temperature becomes sufficiently high marks the transition from a collapsing cloud to a nascent star. Surrounding these embryonic stars, remnants of the molecular cloud persist, forming protoplanetary disks. These disks are crucial in the development of planetary systems, where dust and gas coalesce into larger bodies over time. The intricate interplay between the remnants of molecular clouds and the newly formed stars showcases the cyclical nature of cosmic evolution, providing insight into the continuous birth and death of celestial entities. Gravity serves as the fundamental force orchestrating the transformation of gas and dust into luminous stars. Within these stellar nurseries, gravitational forces begin to dominate the interactions among particles, causing regions of higher density to form. These denser clumps attract surrounding material, amplifying their mass and solidifying their role as stellar progenitors. As the mass accumulates, pressure within the core rises, leading to an increase in temperature that sets the stage for nuclear fusion. This process unfolds gradually, with the initial collapse of a dense core often taking millions of years. During this time, the core continues to attract additional material, while the surrounding gas forms an accretion disk. This disk facilitates the inflow of matter, allowing for the growth of the forming star. Eventually, when conditions reach a critical threshold, a stellar ignition occurs, marking the birth of a new star. Gravity not only influences the formation of individual stars, but also shapes the structure of entire stellar clusters. The gravitational interactions among these young stars can result in various phenomena, such as stellar collisions or the ejection of stars from their birthplaces. These dynamics contribute to the evolution of star populations, revealing the underlying complexities of cosmic architecture. Each stellar cycle, driven by gravity, adds layers to the universe's rich history. Molecular clouds vary significantly, each type contributing uniquely to the process of star formation. These regions, composed predominantly of hydrogen molecules, serve as the essential building blocks for new stars and planetary systems. Dense cores within these clouds are where gravitational forces converge. Giant molecular clouds represent the largest types, often spanning hundreds of light years across. They contain vast quantities of gas and dust, providing ample material for numerous stellar births simultaneously. These clouds present an environment where conditions are optimal for the clumping of matter, gradually forming protostars. In contrast, smaller, less dense clouds, known as Bok globulars, exist as isolated entities scattered throughout the interstellar medium. Their compact nature allows them to remain relatively stable, potentially harboring nascent stars within their confines. Over time, these globules may evolve into more complex stellar systems, contributing further to the cosmic landscape. Dark clouds, by their opacity, obscure the light from distant stars, providing an intriguing glimpse into regions of star formation hidden from view. Observations of these clouds reveal their intricate structures, often illuminated by the faint glow of embedded young stars. This interplay of light and shadow adds depth to the understanding of molecular clouds and their role in the vast cosmos. Every stellar nursery is a complex assembly of components and structures, each contributing to the birth of new stars. Dense cores of gas and dust, known as clumps, serve as the initial sites for gravitational collapse. These regions possess a higher concentration of matter, creating the conditions necessary for fusion reactions to ignite. Surrounding the clumps, lighter and more diffuse areas of gas form the intricate filaments that characterize these environments. These filaments act as conduits, channeling material into the denser regions and facilitating star formation. The dynamic interactions between these structures create a constantly evolving landscape, where filaments may collapse under their own gravity or disperse, influenced by external forces such as shock waves from nearby supernovae. In addition to gas and dust, stellar nurseries are often illuminated by the young stars that emerge from this chaotic environment. This illumination contributes to the unique spectral signatures observed in various wavelengths, revealing the chemical makeup of the clouds. Ultraviolet radiation emitted by these nascent stars can also trigger further star formation, initiating a cascading effect within the nursery. The interplay between these components creates a fragile yet vibrant ecosystem, illustrating the delicate balance of forces at work. Each nursery serves as a testament to the processes that govern the life cycle of stars, echoing the intricate beauty of the universe. The protostar phase marks a critical juncture in stellar evolution. Dense clouds of gas and dust collapse under their own gravity, initiating the formation of a core. This core, composed predominantly of hydrogen, begins to compress, raising temperatures and pressure. Surrounding material coalesces, drawn inward by gravitational forces. As the core's temperature rises, it reaches approximately 1 million Kelvin. At this stage, nuclear fusion remains dormant, yet the region emits infrared radiation, illuminating the dark surroundings. This heat and light signal the transition into a nascent stellar entity, cloaked in the remnants of its formation. A protostar, still shrouded in dust, presents a transient visage, embodying the potential for future brilliance. Jets of gas are expelled along the axis of rotation, emerging from the protostar. These outflows, propelled by magnetic fields, contribute to the complex dynamics of this environment. The surrounding disk of material retains angular momentum, facilitating further accretion onto the growing star. Over several 100,000 years, the core continues to heat, and fusion ignites when temperatures soar past the threshold of hydrogen fusion. This ignition marks the end of the protostar phase, transitioning into a stable main sequence star. The birth of a star signifies not only the continuation of cosmic evolution but also the nurturing of future planetary systems within its gravitational embrace. Accretion disks form as material spirals inward around protostars, a dynamic process characterized by the gradual accumulation of dust and gas. In this region, particles collide and coalesce, driven by gravitational forces and angular momentum. The swirling mass exhibit a varying density, with denser areas becoming potential sites for future planets. Temperature within the disk rises as friction generates heat, leading to the formation of various chemical compounds. Molecules begin to interact, fostering an environment rich in potential for the emergence of complex structures. This celestial assembly operates under the principles of thermodynamics as energy transitions and transforms, molding the nascent system. The intricate balance of forces keeps the disk stable, yet ever-changing. Some regions may collapse under their own weight, forming clumps that will eventually evolve into planetesimals. Others may remain diffuse, serving as a reservoir of material for later accretion. The process is a delicate interplay of attraction and repulsion, where the influences of nearby celestial bodies can disrupt or enhance formation. As the protostar continues to accumulate mass, the surrounding disk becomes a crucible of creation, paving the way for the development of diverse planetary systems. Within this fragile beauty lies the potential for life as emerging worlds form from the remnants of the accretion disk, each with a unique destiny awaiting discovery. Var zou ontwinting today. Radiation pressure plays a critical role in the intricate process of star formation, exerting a force that influences the evolution of these stellar nurseries. As nascent stars ignite, they emit vast amounts of energy in the form of radiation, creating a push against the surrounding gas and dust. This force counteracts gravitational collapse, establishing a delicate balance within the dense clouds. In this region, the interplay between gravity and radiation pressure determines whether a protostar will continue to accumulate material or be dispersed into the surrounding void. The energy output from forming stars can trigger shock waves that compress nearby gas, catalyzing the birth of additional stars. Such interactions contribute to the chaotic yet ordered structure of star clusters, where numerous stellar objects coexist, each at various stages of development. The expulsion of material from these young stars can lead to the clearing of surrounding debris, reshaping the environment. Stellar winds and radiation push away gas and dust, exposing new regions to the possibility of star formation. This continual cycle of birth and destruction fosters a dynamic landscape where the remnants of one generation pave the way for the next. Understanding the nuances of radiation pressure provides insight into the mechanisms that govern the life cycles of stars, illuminating the processes that give rise to the cosmos as it is known today. The breathtaking, the enthertawaz cycles of stars as it is known today. The influence of supernovae on stellar nursery formation is profound and multifaceted. When massive stars reach the end of their life cycles, they undergo explosive events that release vast amounts of energy and material into their surroundings. These explosions create shock waves that propagate through the surrounding interstellar medium, compressing the gas and dust within these regions. Such compression initiates the gravitational collapse of nearby molecular clouds, leading to the formation of new stars. The remnants of supernovae enrich the environment with heavy elements vital for the creation of planets and life as it is known. This infusion of materials contributes to the chemical complexity of subsequent generations of stars, enhancing the potential for planetary systems to form around them. The interplay between the remnants of exploded stars and dense cloud formations establishes a fertile ground for new stellar bodies, showcasing the interconnectedness of cosmic events. The aftermath of supernovae does not merely disrupt, it also rejuvenates. The energy released during these cataclysmic explosions can ignite new star formation, transforming regions previously devoid of activity into vibrant stellar nurseries. Over time, These processes emphasize the cyclical nature of cosmic evolution, where destruction begets creation, leading to an ever-evolving landscape of celestial phenomena. The intricate interplay of stellar winds significantly influences the morphology of molecular clouds. High-energy particles and radiation emitted from nearby massive stars create dynamic environments that reshape these clouds, pushing and compressing the gas and dust. This interaction induces turbulence, facilitating the fragmentation of the clouds into smaller, denser regions. The resulting pressure variations lead to the formation of new stellar objects within the confines of these molecular clouds. Regions of increased density can trigger gravitational collapse, giving rise to protostars. As these protostars evolve, they emit their own stellar winds, continuing the cycle of influence on their surroundings. This process highlights the interconnectedness of celestial bodies and the environments they inhabit. Further from the core, stellar winds create intricate structures within the clouds, forming a network of filaments and voids. These structures can serve as both a nursery and a graveyard for stars. In areas where the winds have eroded material, new stars may struggle to form, while in others, the compression may ignite a new generation of stellar births. This delicate balance underscores the fragility of these regions, as they exist on the brink of transformation. The aftermath of stellar winds is not merely a physical reshaping, but an ongoing narrative of birth, life, and eventual demise, encapsulating the relentless march of cosmic evolution. Magnetic fields play a crucial role in shaping the dynamics within stellar nurseries. These invisible forces govern the movement of gas and dust, guiding the interaction of materials that contribute to star formation. In these regions, charged particles become entangled in magnetic lines, creating a complex web of influence that modulates the behavior of the surrounding environment. Within the denser parts of these nurseries, magnetic fields can prevent the collapse of clouds under their own gravity, maintaining a delicate balance between pressure and attraction. This equilibrium allows for the slow accumulation of mass over time, fostering conditions ripe for the birth of new stars. The intricate interplay between gravity and magnetism dictates how material flows inward. Thus, those magnetic fields also facilitate the formation of structures known as filaments. These elongated formations serve as channels for gas and dust, channeling material towards central regions where stars can coalesce. Fluctuations in magnetic energy can trigger bursts of star formation, leading to clusters of stars emerging in rapid succession. As these stars evolve and interact with their environment, they continue to influence the magnetic landscape. This ongoing process contributes to the ever-changing nature of stellar nurseries, illustrating the profound interconnectedness of cosmic elements. Carbon and dust serve as the essential building blocks for star formation, intricately woven into the fabric of stellar nurseries. These regions harbor vast clouds of gas and particles, where stellar material coalesces under the influence of gravity. An abundance of carbon, formed through earlier stellar processes, enriches the environment of Male, allowing for the formation of complex molecules that play a vital role in the birth of stars. In the cooler, denser regions of these clouds, dust grains act as nucleation sites, facilitating the agglomeration of gas particles. This leads to the gradual accumulation of mass, a precursor for the emergence of protostars. The interplay of temperature and pressure within these environments dictates the dynamics of star formation. As gravitational forces pull matter together, the cores of these regions heat up, igniting nuclear fusion once critical thresholds are reached. The intricate balance of elements defines the characteristics of the stars that emerge. Variations in carbon and dust composition can significantly influence stellar evolution and lifespan, leading to a diverse array of celestial phenomena. These newly formed stars eventually return enriched materials back into the surrounding medium, perpetuating the cycle of creation. The ongoing transformation of carbon and dust remains a fundamental aspect of cosmic evolution, shaping the universe in subtle yet profound ways. The life cycle of a star unfolds within the intricate embrace of gas and dust. Initially, dense regions within a molecular cloud collapse under their own gravity, leading to the formation of protostars. As accumulation of material occurs, temperatures rise, igniting nuclear fusion at their cores. This process marks the birth of a new star, illuminating its surroundings with radiant energy. Once stabilized, stars enter the main sequence phase, where they spend the majority of their existence. During this time, they convert hydrogen into helium, sustaining a delicate balance between gravitational collapse and outward pressure from fusion. This equilibrium persists for billions of years, allowing for the gradual transformation of surrounding materials into a variety of elements. As hydrogen reserves diminish, a star undergoes significant changes. It expands into a red giant, shedding its outer layers and creating beautiful nebulae. Core temperatures soar, leading to the fusion of heavier elements. Eventually, the star's life cycle culminates in a dramatic end, either as a supernova or a more tranquil expulsion of its outer shell, leaving behind a dense core known as a white dwarf, neutron star, or black hole. These remnants contribute to the cosmic landscape, serving as the seeds for future generations of stars, continuing the cycle of creation and transformation within the vast universe. Temperature plays a critical role in stellar nurseries, influencing the conditions necessary for star formation. Within these regions, the interplay of heat and density governs the gravitational collapse of molecular clouds. As particles collide and coalesce, they generate heat, raising the temperature of the core. This process initiates the formation of protostars, where material continues to accumulate, increasing both mass and thermal energy. At temperatures exceeding several million degrees Celsius, nuclear fusion ignites, marking the birth of a new star. The balance of radiation pressure from fusion reactions and gravitational forces maintains equilibrium, allowing the star to persist in these environments. Varying temperatures dictate the types of stars that will form. Cooler areas may give rise to smaller red dwarf stars, while hotter regions can lead to the formation of massive luminous giants. The complexity of these environments is further underscored by the presence of different elements, which influence thermal dynamics. Regions rich in heavier elements tend to cool more efficiently, impacting the rate of star formation. As the temperature fluctuates, it shapes the distribution of stars and the overall morphology of the stellar nursery. This delicate balance of heat and density reveals the intricate processes that drive the birth and evolution of celestial bodies, weaving together the fabric of the cosmos. Chemical composition plays a crucial role in star formation, influencing the characteristics and life cycle of emerging stars. Within these stellar nurseries, balance of elements such as hydrogen, helium, and heavier metals dictates how matter clumps together under the influence of gravity. It is the subtle interplay of these elements that determines the efficiency of the cooling processes, allowing dense regions to collapse into protostars. Variations in composition across different regions can lead to diverse types of stars, Higher metallicity regions often yield more massive stars, which may evolve rapidly and end their lives in supernova explosions. In contrast, regions with lower metal content tend to produce smaller, longer-lived stars. This chemical diversity fosters a wide range of stellar phenomena, from the formation of planetary systems to the creation of neutron stars and black holes. The dynamics within these regions are further influenced by the presence of dust and gas, which facilitate the formation of complex molecules. These molecules play a vital role in cooling the surrounding gas, promoting further collapse and star formation. The resulting stars, in turn, enrich their surroundings with heavier elements through their life cycles, gradually transforming the chemical landscape of the galaxy. Each generation of stars contributes to this ongoing cosmic evolution, continuously shaping the structure and composition of the universe. Observational techniques play a crucial role in unraveling the complexities of stellar nurseries. Telescopes equipped with advanced sensors capture a spectrum of electromagnetic radiation, from radio waves to gamma rays. This range allows astronomers to gather comprehensive data regarding the conditions and processes occurring within these regions. Infrared observations penetrate the dense clouds of gas and dust, revealing hidden star formation that remains obscured in visible light. Spectroscopy analyzes the light emitted or absorbed by celestial objects. This technique provides insights into the chemical composition, temperature, density, and motion of the gas and dust within these nurseries. By examining the shifts in spectral lines, researchers can discern the velocities of material moving toward or away from us, shedding light on the dynamics at play in these formative environments. Interferometry combines signals from multiple telescopes, enhancing resolution and allowing for detailed imaging of these regions. This method enables the identification of protostars, the earliest stage of stellar development. Additionally, space-based observatories eliminate atmospheric distortion, offering clearer views of these vast expanses. Data collected from these observations contributes to simulations and models, predicting the behavior of gas clouds and the life cycle of stars. These studies deepen our understanding of stellar nurseries, emphasizing their significance in the broader cosmic narrative. Each discovery adds a layer to our comprehension of the universe's intricate web. The role of infrared astronomy is pivotal in uncovering the hidden aspects of stellar nurseries. In these regions, dense clouds of gas and dust obscure visible light, rendering traditional observation methods ineffective. Infrared wavelengths penetrate these obscuring materials, revealing the intricate structures and processes occurring within. Telescopes operating in this spectrum provide insight into the formation of stars and planetary systems, illuminating the vibrant activity that thrives in the shadows. This technology reveals a diverse array of phenomena, such as protostellar jets and accretion disks, which are not visible in optical light. It captures the birth of new stars, providing a glimpse into their early stages, where gravity compresses gas and dust into ever-densifying cores. The heat generated by this process becomes detectable in the infrared, allowing astronomers to map temperature variations and identify regions of active star formation. Additionally, it aids in understanding the interactions between young stars and their surrounding environments. Stellar winds and radiation from these nascent stars influence the evolution of their birthplaces, sculpting the surrounding material and triggering further star formation. The intricate dance of energy exchange highlights the dynamic nature of these nurseries, revealing how they foster new life in the cosmos. Insights gained through infrared studies continually reshape our understanding of stellar evolution and the life cycle of galaxies. The Hubble Space Telescope has played a pivotal role in unraveling the intricate processes occurring within stellar nurseries. Observations captured through its advanced imaging capabilities reveal the dynamic interactions among gas, dust, and newly formed stars. These stunning visuals provide a glimpse into the chaotic beauty of regions where stars are born, showcasing the interplay of gravitational forces and radiation. In these nebulae, dense pockets of gas and dust collapse under their own gravity, leading to the birth of protostars. Hubble's ability to capture images in various wavelengths enables scientists to track the subtle changes that occur during this transformative phase. It highlights the delicate balance between the energy emitted by newborn stars and the surrounding material, which can either promote further star formation or inhibit it through intense stellar winds. These observations have revealed the presence of complex structures such as filaments and bubbles, suggesting that stellar nurseries are not static environments, but rather dynamic systems constantly evolving. The details captured by Hubble contribute to a deeper understanding of the conditions necessary for star formation, emphasizing the role of environmental factors in shaping the characteristics of these cosmic regions. Such insights enhance knowledge of how stars contribute to galactic evolution, providing a clearer picture of the universe's life cycle and the intricate web of interactions that govern it. The Spitzer Space Telescope plays a crucial role in expanding this understanding by observing the infrared spectrum, a domain that reveals hidden details obscured by dust in these stellar nurseries. Infrared observations penetrate dense clouds, allowing for the examination of the cooler components of star formation. It captures emissions from molecules and dust grains, providing insight into the earliest phases of stellar evolution. This observational capability unveils the presence of protostars, the nascent stages of stellar development, often shrouded in the surrounding material. By mapping the structure of these regions, it highlights the complex interplay of gravity, temperature, and chemical processes that govern star birth. The data reveals how matter accumulates and contracts, leading to the formation of dense cores that will eventually ignite nuclear fusion. Through its detailed surveys, Spitzer has identified numerous young stellar objects and their associated disks, which are critical for understanding planetary formation. The interactions between these young stars and their environments often result in dynamic phenomena, such as outflows and jets, influencing the surrounding gas and dust. These observations have profound implications for the broader understanding of galaxy formation and evolution. They illustrate how the processes occurring within these stellar nurseries contribute to the overall life cycle of galaxies, influencing their chemical composition and the emergence of future generations of stars. The presence of nearby stars introduces a dynamic interplay within stellar nurseries. Their radiation and stellar winds exert significant influence, shaping the surrounding gas and dust. This interaction can trigger the collapse of nearby molecular clouds, initiating the formation of new stars. As these new entities emerge, they contribute to the complex environment, altering the physical and chemical conditions within the nursery. This region witnesses a delicate balance between the forces at play. Massive stars emit intense ultraviolet radiation, ionizing surrounding gas and creating expansive bubbles. These bubbles can compress adjacent gas clouds, fostering an ideal environment for star formation. Over time, the influence of stellar winds can disperse material, but it also enriches the interstellar medium with heavier elements, synthesized during the star's lifetimes. The evolution of these nurseries is a gradual process, marked by the birth and decay of stars. As massive stars exhaust their nuclear fuel, they undergo supernova explosions, releasing vast amounts of energy and material. This event not only contributes to the enrichment of the surrounding region, but can also trigger a new wave of star formation. In this quiet cycle of birth, life, and death, the interconnectedness of nearby stars shapes the future of stellar nurseries. Each stellar entity plays a pivotal role in determining the fate of the gas and dust clouds, fostering an environment for the emergence of new celestial bodies. The emergence of massive stars within these fragile regions brings forth unique challenges and processes. Intense gravitational forces act upon the surrounding materials, leading to a rapid accumulation of gas and dust. This process fosters an environment where pressures and temperatures escalate to extreme levels. As the core contracts, nuclear fusion ignites, marking the transition from a mere cloud of gas to a luminous beacon of energy. The birth of such stars is not without complications. High-energy radiation emitted during the formation can disperse nearby materials, disrupting the delicate balance required for further star formation. The stellar winds produced by these young giants carry away vast amounts of mass, shaping the surrounding space and influencing subsequent generations of stars. The feedback mechanisms inherent in their existence create a dynamic interplay between creation and destruction, often resulting in the formation of nebulae rich in heavy elements. These processes contribute to the evolution of galaxies, as massive stars enrich the interstellar medium with the byproducts of their nuclear fusion, supernova explosions, marking the end of such stars' life cycles. Disperse these elements across vast distances, seeding future stellar nurseries. It is a cycle of birth and death, a constant reshaping of the cosmos driven by the power and majesty of these newborn giants. Clusters of young stars emerge as luminous beacons within the vast expanse, their brilliance illuminating the surrounding nebulae. This region, often referred to as a stellar nursery, is characterized by dense molecular clouds rich in gas and dust. Within these clouds, gravitational forces initiate the process of star formation, leading to the creation of new stellar systems. Star clusters, particularly those found in the Orion Nebula, serve as a prime example of this phenomenon. Here, thousands of stars, still in their infancy, gather closely together, forming a gravitational bond that shapes their evolution. Each cluster acts as a unique neighborhood where interactions between stars may influence their trajectories and development. The light emitted by these young stars provides vital information about their composition and age, allowing astronomers to study their life cycles. This glow often reveals a spectrum of colors, indicating varying temperatures and stages of development. The presence of surrounding dust and gas contributes to the complexity of these observations, as it can obscure or enhance the light emitted by individual stars. As these young stars age, the dynamics of the cluster evolve. Some may eventually disperse, while others could remain bound together for millions of years, continuing to influence one another's paths through the cosmos. The intricate process of star formation and cluster evolution remains a fundamental aspect of understanding the universe. Binarity plays a crucial role in the stellar formation process, influencing the dynamics within these cosmic nurseries. In regions dense with gas and dust, gravitational forces often lead to the creation of binary systems where two stars evolve in tandem. This close relationship affects their life cycles, impacting the distribution of mass and energy within the surrounding material. The gravitational interaction between binary stars affects their accretion processes. Material from the protostellar disk can be funneled towards one star or shared between them, altering the path of their development. It is within these systems that phenomena such as mass transfer can occur, leading to significant changes in luminosity and composition. Observations suggest that a substantial fraction of stars exist in binary or multiple systems, hinting at the importance of this dynamic in the broader context of galactic evolution. In star-forming regions, the presence of binaries can influence the surrounding environment, promoting turbulence and facilitating the fragmentation of gas clouds. This process can lead to the birth of additional stars, contributing to the overall star formation efficiency. The interplay of gravitational forces ensures that these binary pairs not only shape their own destinies, but also the fates of the stars born in their vicinity. This interconnectedness reveals a complex web of interactions within stellar nurseries, guiding our understanding of the universe's evolution. The feedback mechanisms in stellar nurseries play a crucial role in shaping their evolution. These processes involve the interplay between massive stars and the surrounding gas and dust. When massive stars form, their intense radiation and stellar winds ionize nearby material, creating shock waves that compress the surrounding gas. This compression can trigger the formation of new stars, initiating a cycle of birth and death within these regions. Or this environment, the remnants of supernova explosions contribute further to the dynamics. The energy released during such events disperses material, enriching the interstellar medium with heavy elements. This enrichment influences subsequent star formation, as the availability of these elements affects the physical properties of the gas. Consequently, the cycle of star birth continues, driven by both the remnants of previous generations and the activity of newly formed stars. Dust plays a critical role in these processes as well. It absorbs and re-radiates energy, modifying the thermal balance of the gas. This leads to localized cooling, enhancing the likelihood of gravitational collapse. The intricate balance between heating and cooling establishes the conditions necessary for star formation. These feedback mechanisms illustrate the delicate equilibrium within stellar nurseries, emphasizing the profound interdependence of cosmic phenomena that governs the life cycle of stars and the evolution of galaxies. The presence of young stars introduces significant dynamics within their surroundings. These luminous bodies emit intense radiation and stellar winds, influencing nearby gas and dust clouds. The interaction can lead to the dispersal of material, as the energy released strips away the outer layers of surrounding regions. This process contributes to the gradual alteration of the environment, shaping the landscape of the stellar nursery. In regions where the gravitational pull of young stars is strong, dense pockets of gas may collapse under their own weight, potentially giving birth to additional stars. This self-propagating cycle fosters a continuous generation of stellar offspring, reinforcing the notion that young stars play a pivotal role in the evolution of their environments. The light emitted can also trigger chemical reactions within these clouds, enhancing the complexity of the chemical makeup present. Within this intricate setting, feedback mechanisms operate on multiple scales. The collective influence of numerous young stars can create shockwaves that compress nearby gas, further stimulating star formation. Conversely, intense radiation may halt the process by dispersing material too quickly. The interplay of these forces reflects a nuanced cosmic ballet, where the fates of stars and their environments are inexorably linked, revealing the profound interconnectedness inherent in the universe's vast expanse. Array-breathtaking massive spantab, dust particles permeate these stellar nurseries, acting as essential components in the intricate process of star formation. Comprised of silicates, carbon compounds, and other materials. This fine debris is both a product of earlier stellar generations and a catalyst for new ones. It absorbs and scatters light, creating zones of opacity that shield nascent stars from the harsh radiation of their surroundings. This shielding effect allows gas and dust to accumulate, forming dense clouds that provide the necessary environment for gravitational collapse. Within these clouds, the temperature and pressure rise, fostering conditions conducive to nuclear fusion. The dust plays a crucial role in this transformation, facilitating the cooling processes that enable molecules to coalesce. The intricate balance between light absorption and the release of energy shapes the evolution of these stellar regions, as light from nearby massive stars illuminates the surroundings. It interacts with the dust, generating a complex gradient of light and shadow. The dynamics of this environment are not static. Changes in radiation pressure and stellar winds from nearby stars can disperse dust, altering the conditions for star formation. The remnants of this delicate dance leave behind intricate structures where new stars emerge and old ones fade, marking the continuous cycle of creation and destruction. Each phase offers insight into the processes that govern the life cycles of stars within the universe. The dynamics of stellar feedback play a critical role in shaping the environments in which stars form and evolve. This intricate process begins with the intense radiation emitted by newly born stars. Heat radiates outward, impacting the surrounding gas and dust. As this energy disperses, it alters the thermal balance of the region, creating areas of differing temperatures and densities. Compression occurs in regions where the energy is concentrated, leading to additional star formation. This cycle of heating and cooling fosters an environment rich with potential. The interplay between the intense energy output and the gravitational pull of nearby material drives the continual evolution of stellar nurseries. Conversely, over time, the heated regions cool down as energy dissipates. This cooling allows for the formation of new structures, such as dense molecular clouds, which serve as the next generation of star-forming sites. In this way, feedback loops emerge, where the existence of one generation of stars influences the conditions for future generations. The balance maintained by these processes is delicate. Too much heating can disrupt the formation of stars, while insufficient energy can impede the growth of stellar structures. Understanding this balance reveals the complexity of cosmic ecosystems and highlights the interconnectedness of stellar life cycles in the vast expanse of the universe. The pillars of creation serve as a compelling case study in star formation, revealing the intricate processes that unfold within stellar nurseries. Composed of dense gas and dust, these towering structures are the remnants of ancient stellar explosions. Within their confines, regions of varying density create conditions conducive to the birth of new stars. This region is characterized by immense columns stretching across light years, with some portions experiencing gravitational collapse. As the material within these pillars contracts under its own gravity, it begins to heat up. Interactions between stellar winds and the surrounding material influence the fate of nascent stars. In these formative stages, the balance between radiation pressure and gravitational forces dictates whether a star will continue to grow or be dispersed into the surrounding medium. The pillars themselves are not static. They evolve over time as young stars ignite and carve out their surroundings. This ongoing cycle of birth and destruction highlights the dynamic nature of star formation, emphasizing the delicate interplay of forces that shape the cosmos. Through this lens, the pillars of creation exemplify the transformative journey of matter in the universe. From gas clouds to luminous stars, the timeline of star formation unfolds in several distinct phases, each marked by unique processes and conditions. Initially, vast clouds of hydrogen and helium gas dominate the landscape, known as molecular clouds. Within these dense regions, Gravitational instabilities trigger localized contractions, creating dense cores that begin to collapse under their own gravity. As the core contracts, temperature and pressure rise, initiating the next phase. This protostar stage sees the emergence of a luminous object at the center of the collapsing mass. Surrounding material forms an accretion disk, allowing for further mass accumulation. During this time, jets of material may be ejected, contributing to the intricate interactions within these stellar nurseries. Eventually, the protostar reaches a critical point where nuclear fusion ignites in its core. This marks the transition to the main sequence phase, where it stabilizes and begins its long, luminous life cycle. The star enters a period of equilibrium, balancing the inward pull of gravity with the outward pressure from nuclear reactions. And the star ages. It exhausts its hydrogen fuel, leading to significant changes in its structure. The evolution continues toward red giant or supergiant phases, determined by the star's initial mass. These environments serve as the birthplace of stars, where dense clouds of gas and dust coalesce under gravity's influence. Within these stellar nurseries, complex processes unfold, leading to the formation of new celestial bodies. As material collapses, temperatures and pressures rise, igniting nuclear fusion in the cores of nascent stars. This initiation marks a pivotal moment, as it transitions the surrounding regions from a state of quiescence to one of dynamic activity. The energy emitted by these young stars plays a crucial role in shaping their surroundings. Radiated light and stellar winds disperse nearby gas and dust, influencing the formation of additional stars and planets. This interaction enhances the chemical enrichment of the interstellar medium, contributing to the galactic ecosystem's diversity. It is within these stellar nurseries that the elemental building blocks for life are forged. Heavy elements produced during supernova events eventually find their way into new generations of stars and planets, providing the necessary components for potential habitability. The intricate cycle of star birth and death maintains the balance of matter within galaxies, fostering a continuous transformation. Galactic evolution hinges on the processes initiated in these regions. Their existence underscores the interconnectedness of cosmic phenomena, revealing a delicate balance that sustains the universe's intricate architecture. Chemical enrichment emerges as a significant consequence of stellar nurseries, where the birth of new stars occurs amidst dense clouds of gas and dust. In these regions, the process of nuclear fusion ignites, converting lighter elements into heavier ones, thus altering the elemental makeup of the surrounding material. This transformation is vital for the evolution of galaxies, as it disperses newly formed elements into the interstellar medium. As massive stars exhaust their lifespans, they undergo supernova explosions, releasing vast quantities of energy and distributing their enriched content across the cosmos. This ejection not only contributes to the chemical diversity of the universe, but also provides the building blocks for future generations of stars and planetary systems. The remnants of these stellar nurseries, enriched with elements like carbon, oxygen, and iron, become essential ingredients for the formation of planets and dua. The cyclical nature of star formation and death characterizes the ongoing evolution of galaxies, influencing their structure and composition. These processes ensure a continuous flow of materials, fostering the conditions necessary for the development of complex systems. Observations of various stellar nurseries reveal the dynamic interplay between gravity and radiation, emphasizing the role of these regions in shaping the cosmic landscape. This ongoing cycle of enrichment illustrates the profound impact of stellar nurseries on the universe's chemical evolution. Cosmic rays permeate these regions, serving as high-energy particles that wield considerable influence over star formation. Originating from supernovae and active galactic nuclei, they accelerate through the interstellar medium, colliding with gas and dust. This influx of energy can compress molecular clouds, triggering gravitational instabilities that lead to the birth of new stars. The interaction between these energetic particles and the surrounding environment fosters a dynamic interplay, essential for the evolution of stellar nurseries. The presence of cosmic rays contributes to the thermal balance within molecular clouds, regulating the conditions necessary for star formation. These particles enhance the ionization of gas, facilitating the formation of complex molecules. This chemical richness plays a crucial role in developing protostellar systems. Through their influence, cosmic rays can also drive outflows, which may regulate the mass of newly formed stars and sculpt the surrounding landscape. In these celestial vistas, the impact of cosmic rays extends beyond star birth. They play a pivotal role in shaping the dynamics of entire star clusters, influencing their structure and evolution. This intricate relationship highlights the interconnected nature of cosmic phenomena, where high-energy particles from distant realms interact with the delicate fabric of star-forming regions. Turbulence plays a pivotal role in shaping molecular clouds, acting as the catalyst for star formation. These clouds, composed primarily of hydrogen molecules, exist in a state of dynamic equilibrium, continuously influenced by gravitational forces and thermal pressure. Within this region, chaotic motions create a complex interplay of eddies and currents, fostering areas of increased density. The formation of dense regions within the turbulent flow is crucial for star birth. As clumps of gas contract under their own gravity, they begin to accumulate mass, odeur. Conversely, turbulence can also disrupt the delicate balance within these clouds. Shockwaves from nearby supernovae or the interaction of stellar winds can disperse gas and halt the formation process. The balance between these opposing forces determines the fate of countless stars and the evolution of entire galaxies. Observations reveal that turbulence is not merely a destructive force. It is an essential ingredient in the complex life cycle of molecular clouds. It introduces variability in density and temperature, enabling the diverse conditions necessary for the emergence of new stars and planetary systems. This delicate dance of forces continues to shape the cosmos, revealing the intricate beauty of stellar nurseries. The life cycle of a molecular cloud is marked by phases of formation, evolution, and eventual dispersal. Initially, an accumulation of gas and dust begins to coalesce under the influence of gravity. The temperature fluctuations within this region play a pivotal role in determining the cloud's density. As regions of higher density emerge, they attract additional material, further enhancing their gravitational pull. These denser pockets can collapse under their own weight, leading to the birth of protostars. The surrounding material forms a rotating disk where matter spirals inward, feeding the growing star. This process initiates nuclear fusion, which ignites the core and marks the transition from a protostar to a fully fledged star. Once formed, stars influence their environment through radiation and stellar winds. They can trigger the formation of new stars by compressing nearby areas of gas and dust. In some instances, the stellar life cycle ends in explosive supernova events, scattering elements across the galaxy. These remnants enrich the surrounding medium, contributing to the next generation of molecular clouds. Stellar nursery morphology reveals distinct observational classifications that define various forms of these regions. Each type presents unique characteristics influenced by the surrounding environmental conditions. A prominent category includes dense molecular clouds, where gravitational forces compress gas and dust, initiating the star formation process. These clouds exhibit a complex interplay of temperature, density, and turbulence, shaping their overall structure. Another classification involves reflection nebulae, illuminated by the light of nearby stars. The dust within these regions scatters light, resulting in a soft glow that highlights the intricate features of the surrounding material. Their ethereal appearance masks the ongoing processes of star formation, providing a glimpse into the dynamic interactions occurring within. Emission nebulae also come into play, characterized by their ability to emit light due to ionized gases, often associated with young, hot stars. These regions serve as both the birthplace of new stars and the remnants of their stellar predecessors. The interplay of radiation and gas dynamics creates a striking visual contrast against the backdrop of the cosmos. Finally, some areas display a chaotic morphology resulting from the interactions of multiple stellar phenomena. These regions exhibit a rich diversity of structures, from filaments to voids, illustrating the complex life cycle of matter in the universe. Each classification informs our understanding of stellar evolution and the mechanisms that govern the birth of stars. The presence of dark matter profoundly influences stellar formation processes within these cosmic regions. This invisible component accounts for approximately 27% of the universe's total mass energy content. Its gravitational effects shape the structures that the interaction between ordinary matter and dark matter leads to complex dynamics. Gas clouds collapse under gravity, and the presence of dark matter enhances this process, facilitating the transition from diffuse gas to denser regions where stars can ignite. These interactions are not uniform. They vary based on local density fluctuations, resulting in diverse stellar populations across the universe. In addition to aiding in the formation of individual stars, dark matter plays a significant role in the evolution of entire galaxies. Its distribution affects the movement of stars and gas, influencing the overall structure and behavior of these colossal systems. Understanding dark matter's role provides insight into the larger cosmic web, revealing how galaxies interact and evolve over billions of years. As research continues, the mysteries surrounding dark matter and its impact on star formation deepen. These investigations illuminate the intricate connections between unseen forces and the visible universe, enhancing our knowledge of cosmic phenomena. The formation of exoplanets is intricately linked to stellar nurseries, where dense clouds of gas and dust coalesce under gravity's influence. This process gives birth to new stars, which in turn create the conditions necessary for planets to form. Within these regions, the interplay between radiation and material dynamics dictates the evolution of newly formed planetary systems. The energy emitted by nascent stars alters the surrounding environment, gradually dispersing the remnants of the original molecular clouds. It is within this fragile ecology that diverse planetary systems emerge, often shaped by the unique characteristics of their parent stars. The composition of these stars can significantly influence the chemical makeup of surrounding protoplanetary disks, determining the potential for varied planetary bodies. Observations within stellar nurseries reveal the presence of complex organic compounds, hinting at the building blocks of life. As stars ignite and heat the surrounding materials, these compounds may interact, leading to the formation of solid structures. The resulting planets can exhibit a wide spectrum of environments, from barren landscapes to potentially habitable zones. Understanding these connections deepens insight into the conditions that foster planet formation and the subsequent emergence of life. Exploring the delicate balance between creation and destruction inherent in cosmic evolution. The intricate relationship between stellar nurseries and galactic dynamics reveals the profound forces at play within these vast regions. Stellar nurseries, such as those found in the pillars of creation, serve as the birthplaces for new stars, their gas and dust coalescing under the influence of gravity. This process is not isolated. Rather, It is deeply intertwined with the broader movements of galaxies. Galactic dynamics, characterized by the gravitational interactions among stars, gas, and dark matter, shape the environments in which these nurseries thrive. Regions of high-density molecular clouds often experience compression from nearby supernova remnants or the gravitational pull of neighboring stellar structures. This compression initiates the collapse of the gas, leading to the formation of protostars. The feedback from these newly formed stars, through radiation and stellar winds, can further influence their surroundings, dispersing material or triggering additional star formation in adjacent areas. The cycle of creation and destruction continues, with stellar nurseries contributing to the ongoing evolution of galaxies. As stars age and exhaust their nuclear fuel, they contribute to the ongoing transformation of their surroundings. This region, known for its dense clouds of gas and dust, serves as a cradle for new stellar formations. Observations suggest that, over time, these remnants will continue to enrich the interstellar medium with heavier elements, creating the necessary ingredients for future generations of stars and planets. The evolving nature of stellar nurseries reveals the delicate balance between creation and destruction. Predictions indicate that as massive stars reach the end of their life cycles, they will explode in supernova events, scattering their enriched materials into the surrounding regions. This process not only paves the way for new stellar births, but also influences the chemical composition of future systems, shaping the potential for complex chemistry and people. Current observations from advanced telescopes highlight the dynamic processes within these nurseries. The shifting clouds of gas and dust can be seen interacting, forming intricate structures that indicate ongoing star formation. Future studies aim to enhance our understanding of these phenomena, utilizing both ground-based and space-based instruments to capture the subtle nuances of stellar evolution. The interplay of light and matter within these regions continues to offer insights into the life cycle of stars, revealing the fragile beauty inherent in their existence and the vast potential of the cosmos. The formation processes within stellar nurseries significantly influence the development of star systems and the planets that may orbit them. Dense molecular clouds provide the essential ingredients for star formation, creating environments where gravity can assert its influence as pockets of gas and dust collapse under their own weight. Protostars emerge, initiating the complex interactions that will shape their surroundings. These nascent stars emit powerful stellar winds and radiation, which can alter the chemical compositions of their local environments. The energetic outflows disperse material, enriching the interstellar medium and impacting the formation of future generations of stars and planets. This region serves as a cradle, nurturing the birth of planets while also determining their potential habitability. The dynamics within these stellar nurseries can also lead to the formation of diverse planetary systems, where gas giants and terrestrial bodies coalesce from the remnants of primordial material. The gravitational interactions between forming stars and their planetary companions can result in a myriad of orbits and configurations. Such processes highlight the delicate balance between creation and destruction, fostering environments that can either support or hinder the emergence of life. Von Alibio observes as these phenomena provide invaluable information, allowing scientists to unravel the complex narrative of how stars and planets come into existence, evolving through epochs of creation and transformation. The intricate workings of stellar nurseries serve as crucial components in the cosmic cycle of galactic recycling. Within these regions, the remnants of previous stellar generations enrich the interstellar medium with essential elements. As massive stars reach the end of their life cycles, they undergo supernova events, expelling their contents back into space. This process contributes to the gaseous clouds that can later condense, forming new stars and planetary systems. In this way, it is not merely the birth of new celestial bodies that defines the significance of these areas. The recycling of material propels the continual evolution of galaxies. The elements forged in the cores of dying stars, like carbon, oxygen, and iron, become building blocks for future generations of stars and planets. Analyzing the composition of these stellar nurseries reveals the history of chemical enrichment and the progression of galactic evolution. The dynamic interplay between destruction and creation becomes evident as one observes the varying stages of stellar development within these clouds. Young stars illuminate their surroundings while simultaneously influencing the formation of new stars through their stellar winds and radiation. Each cycle, marked by birth and death, contributes to the grand narrative of the universe, highlighting the interconnectedness of cosmic processes. This constant flux fosters diversity in celestial formations, and yes, the role of gravitational instability in molecular clouds is pivotal in shaping the formation of stars. Within these dense regions, variations in density occur, creating pockets where gravity can exert its influence. Over time, these fluctuations lead to the collapse of gas and dust under their own weight, initiating a process that gives rise to new celestial bodies. As the collapse progresses, temperature and pressure within these areas increase, contributing to further fragmentation. Each fragment may produce a protostar, surrounded by a rotating disk of material that will eventually form planets. This sequence of events underscores the delicate interplay between gravitational forces and the structural integrity of the clouds. In this region, turbulent motions can also enhance the complexity of the environment. These disturbances may compress or disperse material, influencing the rate at which new stars are born. The presence of shock waves, often generated by nearby supernovae, can trigger fresh rounds of star formation, introducing new elements into the mix. The intricate conditions found within molecular clouds highlight the balance between cohesion and chaos. As gravity draws material together, the inherent instability allows for a continuous cycle of birth and rebirth. Each formation adds to the evolving landscape, contributing to the vast tapestry of the cosmos. The result is a dynamic, ever-changing environment that remains fundamental to our understanding of stellar evolution. External forces play a crucial role in shaping the dynamics of stellar nurseries. Supernovae, the explosive deaths of massive stars, inject energy and shock waves into their surroundings. These events compress nearby gas and dust, triggering the gravitational collapse that leads to the formation of new stars. Such phenomena can initiate star formation in regions previously devoid of activity, highlighting the interconnectedness of cosmic processes. In addition, the influence of massive stars within a nursery cannot be overlooked. Their intense radiation and stellar winds contribute to the heating and dispersal of surrounding material. This process can halt the formation of new stars in certain areas while simultaneously fostering activity in others, creating a complex interplay within the fabric of the nursery. Gravity serves as the primary force that governs the collapse of these cold molecular clouds. Yet it is the external pressures that can dictate the pace and efficiency of star formation. This competition between gravitational attraction and external influence results in a delicate balance that defines the life cycle of a stellar nursery. Observations of various regions, such as those found in the Eagle Nebula, reveal how these external forces carve intricate structures into the fabric of these environments. The intricate interplay of forces ensures that stellar nurseries remain vibrant and continually evolving, reflecting the vast and intricate web of cosmic interactions. Within these regions, the formation of brown dwarfs represents a fascinating byproduct of the gravitational forces at work. These celestial entities emerge when a cloud of gas and dust collapses under its own gravity, yet fails to accumulate sufficient mass to ignite nuclear fusion in their cores. This threshold typically hovers around 75 times the mass of Jupiter. When conditions are not met, the result is a star-like object that radiates energy in the form of heat rather than light, surrounded by the remnants of their birthplaces. Brown dwarfs serve as intriguing specimens of stellar evolution. Their atmospheres, composed primarily of hydrogen and helium, often contain trace elements that hint at complex chemical processes. The temperature of these objects remains relatively cool compared to their more massive counterparts, often registering below 1000 degrees Celsius. In the dense environment of a stellar nursery, interactions with nearby stars and gas clouds can significantly influence the life cycle of brown dwarfs. Over time, they may interact gravitationally with other celestial bodies, contributing to the dynamic equilibrium of their surroundings. The presence of these objects adds depth to the study of stellar formation and the diverse pathways that can emerge from the same cosmic material, revealing the multifaceted nature of the universe's evolution. Galactic clusters serve as the grand stages where stellar nurseries play a crucial role in the birth and evolution of stars. Within these vast cosmic structures, gravitational forces bind galaxies together, creating regions rich in gas and dust. This environment facilitates the formation of new stars as the dense molecular clouds within these nurseries collapse under their own gravity. As these clouds contract, temperatures rise, leading to the eventual ignition of nuclear fusion. The nascent stars emerge, often surrounded by rotating disks of material, which may give rise to planetary systems. The interaction between newly formed stars and their surroundings can trigger further star formation, fostering a cycle of cosmic rebirth. In these clusters, the distribution and density of stellar nurseries can vary markedly. Regions of heightened activity indicate areas where gas is abundant, while less active zones reveal the ongoing processes of stellar death and recycling. Such dynamics contribute significantly to the overall chemical enrichment of the intergalactic medium. The impact of stellar nurseries is not confined to their immediate vicinity. Outflows from massive stars can disperse elements throughout the cluster, influencing future generations of stars. This interconnectedness underscores the intricate balance of creation and destruction that defines galactic evolution. The role of these nurseries is fundamental to understanding the life cycle of galaxies themselves. Diversity characterizes stellar nursery environments across the universe. Each region exhibits unique conditions influenced by factors such as temperature, density, and chemical composition. The cold, dense clouds of molecular hydrogen serve as the primary birthplace of stars, with regions rich in dust offering an ideal setting for the intricate processes of star formation. In contrast, other environments, such as those near supernova remnants, create a chaotic landscape where shock waves compress surrounding gas, triggering new generations of stellar birth. Hotter, young stars emit intense radiation, shaping their surroundings and influencing the formation of subsequent stars. This interplay results in various types of stellar nurseries, each differing in size and complexity. For instance, large complexes like the Orion Nebula reveal sprawling structures where countless stars emerge amid intricate filaments of gas and dust. Smaller, isolated regions can also be found in less dense areas, showcasing the adaptability of star formation under diverse cosmic conditions. Galaxies exhibit a range of these nurseries, from the active star-forming regions of spiral galaxies to the more quiescent environments of elliptical galaxies, where star formation has significantly declined. This variation contributes to the overall evolution of galaxies, shaping their characteristics and influencing future generations of stars. The study of these environments provides insight into the intricate web of cosmic evolution. This connection intertwines the formation of stars with the enigmatic force permeating the universe. Stellar nurseries, rich in gas and dust, serve as the cradle for new celestial bodies, while dark energy acts as a driving force behind the universe's accelerating expansion. Observations indicate that regions abundant with star formation also reveal patterns influenced by this unseen energy, suggesting an intricate relationship between the two phenomena. In these stellar nurseries, the gravitational forces at play draw materials together, leading to the birth of stars. The energy released during this process influences the surrounding medium, impacting the behavior of gas clouds. Such interactions may, in turn, respond to the effects of dark energy, contributing to the ongoing restructuring of cosmic architecture. Galactic structures emerge and evolve, revealing how dark energy affects the distribution of matter throughout the cosmos. It is within these dynamic environments that researchers can explore how star formation rates might be modulated by the expansive influence of dark energy. The balance between the gravitational attraction of forming stars and the repulsive force of dark energy creates a delicate equilibrium, shaping the future of galaxies. Understanding these connections deepens the comprehension of cosmic history, revealing the profound implications for the fate of the universe. Each stellar nursery stands as a testament to the complex interplay of forces that govern existence. These regions serve as vital laboratories for unraveling the secrets of cosmic history. Within the dense clouds of gas and dust, the processes of star formation unfold, illuminating the origins of elements that compose the universe. The stellar nurseries are crucial in tracing the evolution of galaxies, as they provide insight into the conditions that foster star birth across different epochs. Observations reveal that these areas are not merely sites of creation, but also of destruction. The massive stars that emerge from these nurseries often end their lives in violent supernovae, enriching the surrounding medium with heavy elements. This cycle of birth and death influences the chemical makeup of subsequent generations of stars and planets, establishing a continuous link through cosmic time. Astrophysicists study these phenomena to better understand the life cycle of matter. By examining the spectral signatures emitted from these regions, they can infer the temperature, density, and composition of the interstellar medium. This information helps reconstruct the timeline of the universe's evolution, revealing how matter coalesces in the wake of cosmic events. The delicate balance between gravity and radiation pressure showcases the dynamic nature of these environments. Each stellar nursery, while ephemeral, plays a pivotal role in the grand narrative of cosmic history, shaping the universe as it expands and evolves. The formation of supermassive black holes is intricately linked to these stellar nurseries. In regions dense with gas and dust, of gravitational forces intensify, leading to the birth of massive stars. Their life cycles are brief yet explosive, culminating in supernovae that enrich the surrounding medium with heavy elements. This enriched material acts as a catalyst for subsequent star formation, fostering an environment ripe for the emergence of more massive stellar entities. These massive stars, far exceeding typical stellar masses, evolve rapidly, collapsing under their own gravity. In certain conditions, this collapse does not result in a conventional supernova, but instead gives rise to black holes, which can grow in mass by accreting surrounding material, as well as merging with other black holes. The remnants of stellar nurseries harbor the potential to become the seeds of supermassive black holes found at the centers of galaxies. This process can take millions to billions of years, with the influence of these massive gravitational wells affecting the dynamics of entire galaxies. They act as pivotal points shaping the orbits of stars and interstellar material, while simultaneously serving as indicators of cosmic evolution. Observations reveal that the largest galaxies tend to harbor supermassive black holes, emphasizing the interconnected nature of stellar nurseries within the cosmic framework. The evolution of stellar nurseries unfolds over vast stretches of cosmic time. Initially, dense regions of gas and dust coalesce under gravitational forces, forming protostars that eventually ignite nuclear fusion. This process marks the birth of new stars, illuminating their surroundings and expelling material that contributes to the nursery's dynamic environment. These regions exhibit variations in temperature and density, influencing the rate of star formation and the types of stars that emerge. For us, as stellar activity progresses, massive stars burn brightly for mere millions of years before exhausting their nuclear fuel, resulting in supernova explosions. These events disperse elements into the surrounding medium, enriching it and fostering the next generation of stars. The remnants of this cycle contribute to the ongoing transformation of the nursery, as existing stars evolve and new ones take their place. Over time, stellar nurseries can transition into more complex structures, often influenced by external factors such as shock waves from nearby supernovae or interactions with neighboring galaxies. These forces can compress gas and dust, triggering bursts of star formation that reshape the nursery's landscape. The vast distances separating us from these stellar nurseries pose significant scientific challenges. Analyzing light that has traveled millions of years to reach Earth requires advanced telescopes capable of capturing faint signals among the cosmic background. This region, rich in gas and dust, obscures many wavelengths, necessitating the use of infrared and radio observations to penetrate the veil. Data collection often involves complex processing techniques to filter out noise, enhancing the clarity of signals emitted by these nascent stars. The interaction dynamics within these clouds remain poorly understood, as simulations struggle to accurately predict star formation rates under varying conditions. Factors such as turbulence, magnetic fields, and the influence of neighboring stars complicate the picture further. Calibration of instruments is crucial. Slight deviations in measurements can lead to substantial discrepancies in the estimated properties of these stellar nurseries. Each observation offers a glimpse into the past, yet the present conditions are often inferred rather than directly observed. Collaboration across disciplines, from astrophysics to computational modeling, is essential to unravel the complexities inherent to these regions. Despite the challenges, researchers continue to refine their techniques, striving to decode the intricate processes that govern the birth of stars. Advances in technology may eventually illuminate the mysteries that have long eluded understanding in the depths of these cosmic nurseries. Enhancements in space telescopes are poised to revolutionize research within stellar nurseries, equipped with advanced sensors and higher resolution capabilities. These instruments will penetrate the dense clouds of gas and dust that shroud the formation of new stars. The clarity afforded by these upgrades enables a more detailed examination of the intricate processes that govern stellar birth and evolution. Spectroscopic analysis plays a vital role in this endeavor. By analyzing the light from these regions, scientists can discern the chemical composition and temperature of forming stars, providing insights into their life cycle. Key elements such as hydrogen and helium, along with trace amounts of heavier elements, reveal the conditions present at the moment of formation. This information contributes to a broader understanding of stellar evolution across different environments. Adaptive optics technology further enhances observational precision, compensating for atmospheric disturbances that obscure celestial observations from Earth. Space-based observatories, free from such complications, will yield clearer images and data, unveiling structures within these cosmic edifices that were previously masked. Collaboration among international space agencies is likely to accelerate the deployment of next-generation telescopes. These commitments signal a shared ambition to unlock the secrets of stellar nurseries, fostering a comprehensive understanding of the cosmos and its myriad wonders. The future of stellar nursery research is bright, promising profound revelations about the very fabric of the universe. Mutere the part, unthorsit basib, naim puge vrossel unthethort, offering a unique collaboration between professional astronomers and the public. Enthusiasts and amateur astronomers contribute valuable data, often enhancing the understanding of these complex regions. They utilize accessible tools, such as telescopes equipped with imaging technology, to capture and analyze the intricate details of star formation. Projects designed for community involvement allow individuals to engage directly with the cosmos. By participating in data collection and analysis, they help unravel the mysteries of these stellar birthplaces. The discoveries made through collective efforts contribute to a more comprehensive understanding of stellar properties and behaviors. Observations made by citizen scientists frequently supplement professional research, providing a wealth of information that might otherwise remain unexplored. In this collaborative framework, platforms for sharing findings and methodologies encourage an ongoing dialogue between experts and laypeople. Such exchanges foster a deeper appreciation for astronomical phenomena and inspire future generations to explore the universe. The contributions of non-professionals in observing stellar nurseries demonstrate the potential for collective intelligence to illuminate the intricacies of star formation. This synergy of knowledge and passion continues to expand the horizons of astrophysics, emphasizing the importance of collaboration in the pursuit of understanding the cosmos. Each observation becomes a building block in the vast edifice of human knowledge. The cultural significance of stellar nurseries extends beyond scientific inquiry, penetrating the very fabric of human history. Ancient civilizations often regarded the cosmos as a reflection of their beliefs, attributing divine qualities to the celestial bodies born within these regions. The pillars of creation, in particular, captured the imaginations of various cultures, symbolizing creation, transformation, and the mysteries of life. These structures, composed of gas and dust, were frequently interpreted as the wombs of the universe, nurturing the birth of stars. In numerous mythologies, they served as metaphors for rebirth, aligning with agricultural cycles and human existence itself. The awe-inspiring sight of stellar nurseries led to various artistic representations, influencing literature, painting, and even architecture, where celestial themes were woven into sacred spaces. As time progressed, the advent of telescopic technology allowed for a deeper understanding of these cosmic formations. They inspired the scientific revolution, generating curiosity about the nature of the universe and humanity's place within it. The exploration of stellar nurseries prompted questions that transcended science, intersecting with philosophy and spirituality. In contemporary society, the study of these regions continues to evoke wonder, providing a bridge between ancient beliefs and modern science. They remind us of our shared heritage, rooted in the stars that illuminate both the night sky and the depths of human inquiry. Artistic interpretations of these structures often reflect their ethereal qualities, capturing the delicate interplay of light and shadow inherent in the gas and dust. Artists strive to convey the surreal beauty of this region, highlighting the majestic columns that serve as cosmic incubators for new stars. Each brushstroke or pixel aims to evoke the sense of wonder that this celestial nursery inspires, encapsulating a moment where science meets imagination. These representations vary widely, from hyper-realistic digital renderings that closely mimic the Hubble Space Telescope's observations to abstract interpretations that emphasize the emotional resonance of creation itself. The colors chosen often mirror the spectral emissions of the nebula, where hydrogen glows in shades of red and oxygen manifests in hues of blue. Such choices enhance the visual narrative, inviting viewers to contemplate the vastness of the universe and their place within it. In literature, the pillars of creation have inspired poets and writers to reflect on themes of genesis and transformation. Metaphors rooted in this cosmic landscape resonate with humanity's own experiences of birth and renewal, bridging the gap between the infinite and the intimate. This delicate balance of science and art fosters a deeper appreciation for these celestial wonders, inviting exploration and curiosity that transcends generations. The legacy of these pillars endures, echoing through both creative expression and scientific discovery. The need for a responsible approach to stellar observation and research is paramount. Ethical considerations shape how scientists interact with these celestial phenomena, guiding their exploration and understanding of the universe. Respect for the delicate ecosystems that form within these stellar nurseries requires a commitment to minimizing disruption. The intricate balance of gas and dust, essential for star formation, demands careful monitoring. Collaboration between astronomers and ethicists fosters a comprehensive framework for responsible research. This region of space, rich with potential, holds not only scientific intrigue, but also a deep cultural significance. The implications of observing these formations extend beyond mere data collection. They touch upon the stewardship of cosmic heritage. The pursuit of knowledge must align with the principles of sustainability, ensuring that future generations inherit a universe that remains as unblemished as possible. Public engagement and transparency have become vital components in the ethical discourse surrounding astronomical studies. Communities often possess a shared interest in the cosmos, enhancing the dialogue between scientists and the public. This interaction encourages informed consent and collective ownership of astronomical heritage. Recognizing the interconnectedness of human curiosity and the vastness of space, it becomes clear that a thoughtful approach to stellar observation not only enriches scientific understanding, but also honors the wonders of existence beyond Earth. The significance of international collaboration in space astronomy cannot be overstated. This shared endeavor brings together diverse expertise, resources, and perspectives, enhancing the capacity for groundbreaking discoveries. The vastness of the cosmos often presents challenges that no single nation can tackle alone. Collaborative missions allow for pooling of funding, technology, and research, fostering an environment where innovation thrives. Joint observatories and satellite missions exemplify this cooperative spirit. The Hubble Space Telescope, an initiative involving multiple space agencies, serves as a testament to what can be achieved when nations unite under a common goal. It has provided invaluable insights into the nature of distant galaxies, nebulae, and phenomena such as black holes. These revelations not only deepen comprehension of cosmic structures, but also underscore the importance of unity in scientific pursuit. Data sharing further amplifies the impact of these collaborations. Researchers from various countries contribute to a global database, enabling a more comprehensive analysis of celestial events. This sharing of knowledge enhances the accuracy of models and predictions, leading to a richer understanding of the universe. The collective efforts of astronomers, astrophysicists, and engineers facilitate groundbreaking advancements, gradually unraveling the mysteries of the cosmos, while reinforcing the shared human endeavor to explore the unknown. Technological advancements have catalyzed a new era in stellar research, enhancing the precision of observations and deepening the understanding of cosmic phenomena. Innovative instruments, such as high-resolution spectrometers, allow for the analysis of light from distant stars, revealing their composition, temperature, and motion. These instruments transform the faint signals from stellar nurseries into coherent data, illuminating the processes of star formation and evolution. Improvements in imaging technology enable astronomers to capture intricate details of nebulae and their surrounding environments. Observations are no longer limited to visible light. The introduction of infrared and radio wavelengths provides insights into cooler regions of space, where clouds of gas and dust conceal nascent stars. This expanded view reveals the intricate structure of stellar nurseries and the various stages of stellar birth. Computer simulations play a critical role in modeling the complex interactions within these regions. By simulating the dynamics of gas and dust under different conditions, scientists can predict the formation and life cycles of stars with remarkable accuracy. Collaboration among observatories worldwide fosters an integrated approach, leveraging the strengths of diverse technologies. Each advancement builds upon previous discoveries, creating a continuous flow of knowledge. This collective momentum enriches the field, revealing the delicate balance between creation and destruction inherent in the life of stars. Public engagement plays a crucial role in advancing the understanding of astrophysics. It fosters a connection between complex scientific concepts and the general populace, cultivating a community that values exploration and discovery. In this realm, shared knowledge can spark curiosity, leading to increased support for research initiatives and funding opportunities. Educational outreach transforms abstract theories into tangible experiences through planetarium shows, interactive exhibits, and citizen science projects. Individuals can participate in real-time data collection and analysis. This involvement not only enhances learning but also democratizes science, allowing diverse voices to contribute to the ongoing narrative of the universe. One seeks to depare beyond traditional boundaries. Online platforms facilitate discussions that connect scientists with enthusiasts from around the globe. This interaction nurtures a culture of inquiry where questions can be posed freely and knowledge disseminated rapidly. The influence of social media has further amplified this dialogue, breaking down barriers that once separated experts from the public. Collaborative efforts often lead to innovative solutions for complex problems. When individuals from various backgrounds unite under a common interest in the cosmos, new ideas flourish. Such synergy reinforces the notion that understanding our universe is not solely the domain of academics, but is a shared endeavor, enriching both personal and collective experiences. Viewing minds together, they forge a path toward deeper comprehension of the cosmos. The emerging field of astroinformatics has begun to reshape the methodologies used in stellar studies. This new discipline harnesses sophisticated algorithms and vast databases, enabling researchers to analyze astronomical data with unprecedented efficiency. In this realm, it becomes possible to sift through millions of celestial observations, isolating patterns and extracting meaningful insights from the noise. Data gathered from telescopes and satellites feeds into complex systems, where machine learning techniques can identify the characteristics of stars and their surrounding environments. The intricate relationships between various cosmic elements are revealed through this analytical lens. This process not only enhances understanding, but also facilitates the discovery of previously unrecognized phenomena. In this context, each dataset acts as a window into the life cycles of stars and the dynamics of their formation. The meticulous analysis of light curves, spectra, and spatial distributions illuminates the processes driving stellar evolution. Over time, these insights contribute to a more nuanced understanding of the interactions within stellar nurseries and the conditions that foster the birth of new celestial bodies. As astroinformatics continues to evolve, it brings with it the promise of illuminating the darker corners of the universe. This quiet revolution in data analysis serves as a catalyst for new hypotheses and explorations in the vast expanse of space. The role of machine learning in identifying stellar nurseries has emerged as a pivotal advancement in astronomical research. These systems analyze vast datasets collected from observatories and space telescopes, extracting patterns that may elude human researchers. Complex algorithms process infrared images, revealing regions dense with gas and dust, where stars are born, the scarce prunei. This capability allows for the identification of stellar nurseries that were previously unnoticed, expanding the catalogue of these celestial phenomena. Within these regions, the interplay of gravity and gas dynamics facilitates the birth of new stars. The intricate structures formed during this process, often referred to as filaments and clumps, provide insight into the mechanisms of star formation. Machine learning enhances the understanding of how these structures evolve over time, offering predictions regarding future stellar development. The integration of artificial intelligence streamlines the classification of various types of stellar nurseries, from those exhibiting vigorous star formation to quiescent regions holding potential for future activity. This efficiency accelerates research timelines, enabling astronomers to focus on deeper questions regarding the life cycle of stars and the impact of environmental factors. As these advanced analytical tools continue to evolve, the interpretation of data will further refine our understanding of the universe's earliest stages, illuminating the delicate processes that give rise to the stars that populate galaxies. Recent discoveries within stellar nurseries reveal intricate details about the birth and development of stars. Observations from the Hubble Space Telescope have provided insights into the regions known as the pillars of creation, where dense clouds of gas and dust serve as incubators for new stars. In this region, the interplay between gravity and radiation leads to the formation of protostars, each a potential beacon of light in the cosmos. The analysis of this area has uncovered a variety of stellar ages and evolutionary stages, allowing scientists to piece together a timeline of star formation. Spectroscopic studies indicate that some of these fledgling stars are surrounded by disks of material, hinting at the potential for planetary formation. Each of these disks holds clues to the processes that may lead to the emergence of solar systems. Further investigations have demonstrated the role of turbulence within these clouds. The chaotic motions influence the rate of star formation, with more turbulent regions potentially hindering the gravitational collapse that creates stars. Observational data suggest a correlation between turbulence levels and the distribution of young stellar objects within these nebulous environments. These findings not only deepen our comprehension of star formation, but also enhance our grasp of the fundamental principles governing the life cycle of matter in the universe, bridging the gap between the cosmic and the terrestrial. Advancements in technology are poised to revolutionize star formation research. The deployment of next-generation telescopes, such as the James Webb Space Telescope, will provide unprecedented insights into distant stellar nurseries. Observations at various wavelengths will reveal the intricate processes of star birth, illuminating aspects previously shrouded in darkness. This region of cosmic evolution remains a focal point for theoretical models. Simulations utilizing high-performance computing will offer valuable predictions about the conditions necessary for star formation. These models will incorporate factors such as magnetic fields, turbulence, and the influence of surrounding interstellar material. As data collection becomes more sophisticated, correlations will emerge, refining existing theories and potentially leading to new paradigms in astrophysics. Collaborative efforts among global research institutions will foster a more holistic understanding of stellar evolution. By pooling resources and data, scientists can develop comprehensive databases that encompass a wider range of stellar environments. This cooperative framework will facilitate cross-disciplinary investigations, linking stellar formation to galactic dynamics and the cosmic web's structure. The continued study of these enigmatic regions is integral to our broader understanding of the universe. As research progresses, new questions will arise, driving exploration deeper into the mysteries of star formation. Each discovery will pave the way for further inquiries, illuminating the celestial processes that forge the stars that light our night skies. Stellar nurseries serve a critical role in the larger framework of cosmic structure formation. Within these regions, dense clouds of gas and dust collapse under their own gravity, giving rise to new stars. This process not only generates individual celestial bodies, but also influences the gravitational dynamics of their surroundings. Young stars emit intense radiation, dispersing surrounding material, which can trigger further star formation in neighboring regions. These interactions create a feedback loop where the birth and death of stars continually reshape the interstellar medium. The remnants of massive stars, such as supernovae, enrich the surrounding gas with heavy elements, contributing to the chemical evolution of future generations of stars. Over vast timescales, these processes lead to the organization of matter into galaxies, clusters, and larger cosmic structures. The intricate balance of gravitational forces and radiation pressure in stellar nurseries also dictates the morphology of galaxies. Spiral arms, for instance, can be traced back to regions of active star formation, where gas density peaks. Beneath context, the study of stellar nurseries not only enhances understanding of individual star formation, but also provides invaluable insights into the broader evolution of the universe. Observations of these regions reveal the ongoing narrative of cosmic history, intricately woven through the fabric of space and time. Gravitational lensing serves as a powerful tool for observing distant stellar nurseries, bending light from objects situated behind massive foreground galaxies. This phenomenon allows astronomers to gain insights into regions that would otherwise remain hidden from view. By analyzing the distorted images produced, it becomes possible to study the early stages of star formation, unveiling processes that occurred billions of years ago. The influence of gravity on light is essential in understanding cosmic structures. Massive clusters of galaxies act as cosmic lenses, magnifying the light emitted from distant nurseries. These interactions enhance the brightness and detail of celestial objects, allowing for clarity in observation. The distortions created serve not only to reveal the presence of stars and gas, but also to provide information about their composition and formation conditions. In this context, the cosmic dance of light and gravity unveils the intricate networks of gas and dust that cradle newborn stars. The environmental conditions surrounding these formations are crucial as they dictate the rate of star formation and the eventual fate of these celestial bodies. Each observation through gravitational lensing enriches the knowledge of stellar evolution, offering a glimpse into the early universe and the fundamental processes that shaped it. The delicate balance of forces at play illustrates the complex dynamics governing the birth of stars. The integration of theoretical models and observational data reveals profound insights into these stellar nurseries. Sophisticated simulations provide a framework for understanding the processes occurring within regions like the pillars of creation. These models account for variables such as gravity, radiation, and gas dynamics, enabling researchers to predict the formation and evolution of stars with increasing accuracy. Observations from advanced telescopes add a crucial layer of validation to these theoretical constructs. High-resolution imaging allows for the examination of gas and dust distributions, revealing the intricate structures that harbor nascent stars. This region, rich in hydrogen and other elements, serves as a crucible where stellar birth occurs. The interplay between the observed morphology and the predicted behaviors of matter helps to refine the underlying theories. In addition, spectral analysis of light emitted by these regions offers clues about temperature, composition, and motion. Such data enhance our understanding of the physical conditions that facilitate star formation. By comparing simulations with real-time observations, a clearer picture emerges, illustrating the life cycle of stars from initial collapse to ignition. The collaboration between theory and observation fosters a deeper comprehension of the processes shaping the cosmos. This synergy is essential in unraveling the mysteries of stellar evolution. The significance of stellar nurseries extends far beyond the birth of stars. These regions serve as critical environments for the formation of molecular clouds that harbor the ingredients necessary for the genesis of planets. And as stellar winds and radiation from newly formed stars compress surrounding material, the intricate processes of chemical reactions initiate, leading to the formation of complex molecules. This gradual evolution contributes to the diverse chemical landscape observed in protoplanetary disks, where the potential for planet formation is realized. The interaction of intense ultraviolet light with the surrounding gas fosters a dynamic atmosphere where various compounds undergo transformation, yielding a rich environment that could support prebiotic chemistry. The potential for these environments to harbor conditions similar to those found on Earth opens avenues for understanding life's origins beyond this planet. Astrobiology studies the parallels between these stellar nurseries and other celestial bodies, seeking to identify markers of habitability. This line of inquiry not only enhances the comprehension of our own solar system's formation, but also illuminates the possibilities of life elsewhere in the universe, revealing the profound interconnectedness of cosmic processes. The pillars of creation serve as a poignant reminder of both the fragility and resilience found within stellar nurseries. These immense clouds of gas and dust harbor the beginnings of stars, illustrating the delicate balance between creation and destruction. Within these towering formations, gravity pulls matter together, while intense radiation from newly formed stars begins to erode the surrounding material. This interplay shapes the life cycle of stars, making it a constant cycle of birth and decay. It is within these regions that new elements are forged, contributing to the chemical richness of galaxies. The remnants of ancient supernovae enrich the interstellar medium, providing the building blocks for future generations of stars and planetary systems. This ongoing process underscores a continuous cycle of renewal that characterizes cosmic evolution. The visual beauty of these structures, with their intricate filaments and glowing edges, belies the harsh conditions present in stellar nurseries. Intense radiation and violent winds challenge the formation of stable structures. Yet, it is this very instability that, in contemplating the pillars of creation, one finds an exquisite balance between fragility and strength, illustrating the dynamic nature of the universe and its ability to create, despite the ever-present forces of destruction. It beckons researchers to delve deeper into the mechanisms driving stellar formation within these colossal structures. Observations through advanced telescopes provide insights into the processes of gas and dust accumulation, revealing the intricate interactions that lead to star birth. This region, rich in molecular clouds, serves as a natural laboratory for studying the conditions necessary for the genesis of stars. With the advent of next-generation space observatories, The study of these pillars will expand significantly. High-resolution imaging will unveil previously hidden details, allowing scientists to observe the evolution of protostars and the surrounding material. Such investigations will enhance understanding of how environmental factors influence star formation, including radiation pressure and magnetic fields. Computer simulations complement observational data, offering predictive models of stellar life cycle stages. These simulations can elucidate the impact of feedback mechanisms on surrounding gas, potentially revealing pathways to new star clusters and the eventual fate of these pillars. The shifting dynamics of these formations raise questions about the cyclical nature of cosmic structures, inviting exploration into the life cycles of stellar nurseries. As knowledge deepens, so too does the appreciation for these regions. They embody the delicate balance of creation and destruction, sustaining a cycle that shapes galaxies and influences the evolution of the cosmos itself.